All right. Well, good afternoon, everyone. Happy Election Day. Welcome to today's EOL seminar. If you don't know me, I'm Sarah Woods, and on behalf of EOL, I'm pleased to introduce Dr. Gijs de Boer. Dr. de Boer received his bachelor's from Cornell before pursuing a master's and a PhD in atmospheric and oceanic sciences from the University of Wisconsin-Madison. After completion of his doctoral degree, Dr. de Boer served as a postdoctoral fellow and research scientist at Lawrence Berkeley National Lab. In 2011, Dr. de Boer moved to the Cooperative Institute for Research in Environmental Science at the University of Colorado Boulder. During his tenure at CU, he has served various scientific roles, including Associate Director for Science and Chief Scientist of Integrated Remote and In Situ Sensing. Most recently, Dr. de Boer has served as a Director of National Laboratory Partnerships for the Research and Innovation Office at CU and as a member of the Board of Directors for CoLabs. Dr. de Boer has an impressive resume of accomplishments, so I will highlight two. He received the Presidential Early Career Award for Science and Engineering and several NOAA awards for achievements such as the first deployment of a fully autonomous system for the measurement of vertical profiles of aerosol cloud and meteorological properties. In January of 2025, Dr. de Boer will take up a new position as chair of the Environmental and Climate Science Laboratory Sciences Department at Brookhaven National Laboratory. As many surrounding the EOL community, Gijs is no stranger to fieldwork. He has been involved with over 15 field campaigns, including those funded by NSF, NASA, and DOE. His research focuses on improving understanding of the Earth system, specifically key processes related to the Earth's atmosphere and surface, the interactions between them, and the impact of such interactions on planetary weather and climate. The field objective includes work with both crewed and uncrewed aircraft systems, with observations spanning the globe, from the tropics to the Arctic Ocean, including deployment of remote and in situ sensors from ship, ice, and land. Please join me in welcoming Dr. de Boer for his seminar on learning to fly.
All right, thank you, Sarah. Good afternoon, everyone. I usually like to take a deep breath before seminars, but given that it's November 5th, I thought maybe we would all just take a deep breath together, if you'd like. So just, in through the nose and out through the mouth. Hopefully that helps. Thanks, this was a wonderful introduction. I'm really glad to be here, excited to share some of the work that we've been doing at the University of Colorado with some of our robotic friends. And before I start doing that, though, I wanted to share a little bit more about myself. I find that oftentimes our scientific introductions are great, but they're only about this deep. And this is something that I've picked up working in the international science community, where sometimes, we say where we're from, what we do, 30 seconds of this and that's about it. And you don't really get to know anyone very well that way. But as you might have guessed by my name, I'm not from around here. I was born in the Netherlands, initially raised in the Netherlands. It does sometimes look like this. It's a beautiful place. I encourage you to go visit in the springtime. And I was living there, and clearly my parents had no intention of moving to the US, given that they named me Gijs. It's not a very friendly name for English-speaking people. My father was a ship captain. He sailed around the world in vessels like this. This is the Kieldrecht, which is a bulk cargo carrier. And he was perfectly happy doing that. But once my two sisters were born, I think he decided that being gone for 7 or 8 months at a time wasn't a great fatherly role model way of living. So he checked in with his company and asked whether there might be any desk jobs available somewhere, and that's what brought us to the US. So in 1985, I hopped on a plane just like this one and flew from Amsterdam to New York. And that's kind of how I ended up where I am now, just from a location perspective. I think if I'd stayed in the Netherlands, who knows what I would have ended up doing. But lived a relatively normal life growing up, I think. Played sports, enjoyed living in the Northeast and going to school and things like that. Went to college, as Sarah said. I went to Cornell University and spent my summers not in Ithaca, but actually back on the docks. When you have a father who's in the shipping industry, that's the sort of jobs you're handed. So I ended up working as a longshoreman in the Port of New Haven, which is pictured here, which is actually fun. It wasn't that bad. It wasn't as bad as you might think, but it also told me that I didn't want to spend my life in hard labor. And I got an internship working with this guy. For those of you who are from the Northeast or have spent time in Connecticut in the 70s through the 90s, you might know Dr. Mel Goldstein, who was working at Channel 8 at that time in New Haven. I spent a summer doing morning show graphics with him for the news. Had a great time, but that pretty quickly taught me that I also didn't want to be a TV meteorologist, which is kind of what I was going to school for. And so I started looking at other options, and it turned out that during my last summer at Cornell, I got an internship at the Northeast Regional Climate Center, working with some of the team there and starting to kind of dive into research. That was really timely because when you graduate from college, you kind of have to make some decisions, and graduate school was at that point a good decision based on how much I liked doing what I was doing at the NRCC. So I went to the University of Wisconsin. My first work was with the LIDAR group there, Ed Elaranta and his team. Some of you may know Ed. And I spent a lot of time looking at cold air outbreaks over the Great Lakes. There was a really nice data set from a campaign called Lake Ice that happened in the late 90s. And I split my time between the LIDAR group and modeling group run by Greg Tripoli, formerly run by Greg Tripoli at the University of Wisconsin. And initially was doing things focused on coastal circulation, so land breeze circulation. And it was at that time that I became really interested in lower atmospheric processes, and also at some level in aircraft-based research, because one of the aircraft, may be familiar to some of you, that was out there, of course, was sampling the lower atmosphere over the Great Lakes. And it seemed like a great idea until I talked to the people who were actually on the aircraft, and they said, man, I've never been sicker flying through the cold air outbreak convective boundary layer over the Great Lakes in the wintertime, bouncing around for hours at a time. So that was maybe the first time I had a light bulb go on to say, well, maybe we can send aircraft up there without making people sick. And then from there, I went on to study Arctic processes, and that was a little bit coincidental because we had one of our LIDAR systems go up to northern Alaska and had just collected a great data set, and I had some wise graduate students tell me, work with the data we have, don't anticipate we'll get more of it. And so I ended up looking at Arctic clouds for my PhD dissertation. And this was also when I learned about this aircraft, the Citation, the UND Citation, having an unfortunate incident in northern Alaska and people having some challenges because the aircraft was forced to ditch due to some icing challenges that it ran into. So again, I had this light bulb go on to say, we really need these measurements, but maybe there are safer ways or different ways that we can do this. So from there, I went to Berkeley Lab. I continued to work on Arctic clouds and really got into the kind of interactions between all of these different processes happening in these complex systems, some of which are outlined here. You can see things like the thermodynamic structure, of course, the surface fluxes, the top of cloud radiation, the aerosol and ice nucleation processes. All these things come together to drive the life cycle of these mixed phase clouds. And while I was studying these clouds, again, I realized that we had bits and pieces of these quantities, but we didn't have it all put together. And part of that was just that we didn't have regular profiling measurements, or we didn't have measurements in challenging to sample locations. And that's when the light bulb really started going off about possibly deploying small robotic aircraft. And I happened to be in a good situation. For those of you who have read the book Outliers, you might know what I'm talking about here when it comes to opportunity. If you haven't, I recommend reading it. It's an interesting book about how people or groups get to where they are. And so there's this part about opportunity which talks about having these favorable or advantageous circumstances that allow you to progress at a rate different than others, and that these opportunities can arise from various factors, including the timing, resources available, connections, and external support. And so it just so happened that I was getting really interested in all this stuff during what I would consider to be a little bit of a golden age of miniaturization, right? You had some guy yelling about this new device that might do something interesting at some point. And cell phones have driven a lot when it comes to making things smaller, right? We have now mass market, small sensors, better battery technology, et cetera. So we owe a lot in our capabilities to the kind of mass electronics advancement of a lot of the types of sensors and equipment that we need. At the same time, I was transitioning to the University of Colorado, and there I had a chance to interface with a group that had been already doing some of this work for quite some time to sample severe weather around the Midwest. So Brian Argro and Jack Elston and others around the area had been working to deploy UAS into severe weather scenarios to collect data where other aircraft just weren't going to be flying very often. And with all of this, I also happened to be fortunate that I was able to get some funding right away from the Department of Energy to start exploring some of these deployments. I will say it was a bit unfortunate that my first place to try all this was in northern Alaska. It's not the easiest place to make things happen, but we did learn quite a lot flying up there and starting to develop and advance these systems. So that's kind of how I got to essentially putting UAS to work for atmospheric science. And over the years, I've worked with a lot of different people, some of whom are in the room here, to help make this happen. And you know, if your face is not up here, it's not because I don't value your contributions to the work. It's just that this has been the group of people who have most closely worked with me on advancing these technologies. And you can see it's a really great combination of individuals from University of Colorado, from NOAA, and other groups. And we've had a lot of good partnerships along the way as well. I've tried to put many of those down here. NCAR, of course, has been a great partner in helping to advance some of our sensors and deploy some of our equipment in the area. It's been a good group to work with. So for the rest of the seminar here, I'm going to talk a little bit about some of the more recent measurement campaigns that we've conducted. We've been to a variety of places across the globe. I don't know that our team has been to the Southern Hemisphere yet. We'd love to do that, but for the time being, these are some of the places that my projects specifically have covered. And today I'm going to talk about the ones in green here. I'll talk about some of the names later, but just to give you a little bit of a geographic overview of where we're talking about for today's measurements. And a lot of the data that I'm going to show today come from one common platform, that is the University of Colorado Raven system that's pictured here and was pictured on the title slide. This aircraft was developed in about 2018, 2019, initially for the storm chasing work that I alluded to earlier. And the reason that we went to this aircraft was that for a long time, the University of Colorado was flying what was known as the Twister aircraft, which was a very capable, very fast, very agile aircraft, but challenging to fly, composite materials, challenging to get up into the air. And so when you're chasing severe storms, you don't have a lot of time. You don't have the luxury of, having a half hour or more to get up to collect your measurements. And so we wanted to develop something that could be put in the air in 5 minutes or so, 5 to 10 maybe, was extremely robust and durable. And so you can see the body here is made of a foam material that's the same kind of foam that you find in vehicle bumpers. So it's a very rugged material. It's still very lightweight, but can take a few bumps. And when you're flying in extreme conditions, that's important. So over the years, we worked to instrument this with a variety of different sensors, and many of those are kind of indicated here. I'll point out a few of them. So on the nose here, we have a multi-hole pressure probe so that we can measure the aircraft's angle of attack and side slip. This particular probe was developed by Black Swift Technologies. It's no longer sold, but we've worked to develop our own at this point, a 9-hole probe that we're flying. This is a fine wire array that was also developed at CU. It has both hot and cold wires so that we can get very fast information on temperature and velocity of the air through the sensor. The aircraft pitot probe is on board for airspeed measurements. We have, difficult to see, but you see this little dot here. We have a similar one on the bottom. These are IR thermometers, narrow field of view, so that we can get an idea of whether we're flying over ground interfaces, things like shorelines or other things that would have a temperature footprint for the sensor to measure, or whether we're flying under cloud or not, which can be quite interesting at times. And then we have these pair of Weissler RSS 421s that we have mounted at different angles to avoid solar exposure. They're sitting in the airflow over the aircraft and are ventilated pretty efficiently. We've worked with Terry and others to help integrate these systems. I will mention also quickly that we had a fun thing a few years ago. We had a campaign in the Crested Butte area, and we decided we would make all of our platforms into superheroes. So Raven is also known as Winged Wonder, and we've used this in a variety of different outreach capacities. So looking quickly at the performance of the Raven, this is a figure from a recent paper that we published based on a few weeks of observing at the ARM Southern Great Plains site. The different colors on this figure represent measurements from different aircraft against ground measurements or radiosondes. The gold-colored dots are the Raven measurements, and I'm not standing here to point out that one aircraft is better than another, but rather to say, if you look at this critically, the measurements are generally very close to that one-to-one line. There are sampling differences, of course. You never expect them to be perfect, but in general, you see what you would expect to be good agreement between the kind of surface-based sensors or the radiosonde-based sensors and our aircraft. And we've also spent time looking just at very individualistic kind of temporal comparisons. This is our aircraft in the golden color flying around the 60-meter tower that ARM has deployed there. So looking at things like the wind components and temperature from this flight. You can see the aircraft has more variability in the measurement. That's not surprising. It's moving through the air and sampling features multiple times over as the tower is just sitting there letting things advect by. But you can see that in general, things are well aligned. There aren't major biases and things like this. Finally, just a quick plot looking at some of our flux measurements. So this is showing sensible heat flux from our platform, which is the second one here. This top one is from the Black Swift S0 aircraft, but all these gold dots represent our measured fluxes, sensible heat flux in this case, relative to the tower-based measurement from the sonic anemometer, and then some of the co-spectra down below there. So I'm going to talk about a few different campaigns here, the first of which is the Atlantic Trade Wind Ocean Atmosphere Mesoscale Interaction Campaign. It is a significant mouthful of words, but we were tasked with sampling frequently the subcloud layer in the tropical trades to better understand the surface fluxes coming off of the ocean and how those impact the boundary layer and cloud development. So we got to spend a little over a month on a beach in Barbados. It was awful. I never want to do it again. Actually, I will say we got blasted with salt, and that was not so great for us and not so great for our aircraft, but I can't complain too much ultimately. And you can see where we were flying. This is the area that we were flying in off of kind of northeastern Barbados here. If you zoom in, you can see all of our flight patterns. These legs are roughly 2.5 to 3 kilometers across. So we were operating in the near shore environment, not too far offshore, but sampling very regularly, 2 to 3 flights per day, and sampling different altitudes to get statistics on properties. And I'm going to show a little animation here from the aircraft. We had a camera on board for some of our flights, just because I think it's a nice indication of the sorts of measurements we're collecting, right? So here we're flying at a given altitude for about 10 to 15 minutes at a time to collect statistics, to be able to calculate fluxes across that boundary. And one of the major benefits that we have using these aircraft is that we were flying at relatively slow speeds, right? The cruise speed of this aircraft is about 17 meters per second. So when you have sensors on board sampling at 400 hertz, you're sampling very small features at that point. And you have the ability to kind of carefully pick your positioning relative to features of interest, like cumulus clouds in this instance. We spend a lot of time flying at cloud base or just below, and a lot of time just sampling that near cloud environment. So this video goes on for about 2 hours. That was the endurance of the aircraft, but I'm going to keep going because we don't have that much time. Here are some examples of measurements from our platform. So on the left there, you see a figure from a paper by Boer and Stevens that was giving an overview of the Eureka and atomic field campaigns. The top part of that figure, so from the zero line up, is from the Raven. Those are, I believe, potential temperature, if I remember correctly. Oh yeah, it's down on the bottom there. So we've got potential temperature measurements, color-coded by humidity over the entire campaign. So you can see there wasn't a ton of variability over the campaign. You can see some of the variability happening at individual heights. That's when we're spending a long time at a given height. And you can see that in the right figures there as well. One of our things that we were doing was comparing cases where we had more versus less cloud cover. So in this case, looking at a basically cloud-free day versus one where we had about a third of the sky covered in clouds. You can see a variety of different things in these figures, but I'll point out just the variability that you see when you stick around a level for a while versus just sampling through it, right? And this is something that is difficult to do in a single location with either the larger aircraft or with balloons, because you're either covering much larger distances or you're just sampling through with individual profiles and not really getting that local variability that we see if we're just doing these local legs close by. And finally, I'll point out a figure from a paper by Luis Nayens that leveraged our Raven data to look at momentum fluxes between the surface and cloud base, and also use those in combination with those from the French ATR-42 aircraft. So you can see there's very good alignment between the two platforms. Here, these are broken up by date, but the date here is a proxy for cloud cover. So these are different cloud cover regimes, and understanding the role of the momentum flux in these different regimes was part of the work that we conducted here. A second relatively recent project was the TRACER campaign, Tracking Aerosol Convection Interactions experiment that took place in the Houston area in the summer of 2022. And the top right figure there is kind of a conceptual diagram of our role in this. We partnered with the University of Oklahoma, who developed the Coptersonde quadcopter system. And we had aircraft flying at two different sites, one down here near the Brazoria National Wildlife Refuge, south of Houston, and the other at the University of Houston Coastal Center here in Lamarck, Texas. And again, we did kind of these longer 2-ish kilometer transects to capture statistics at different heights, primarily to look at the influence of the Gulf of Mexico sea breeze as it made its way inland on the lower atmosphere. And for this particular campaign, one of the things that we did was install a POPS system. The POPS is an optical particle spectrometer, a small one. We worked with the NOAA Chemical Sciences Laboratory to integrate that onto the Raven. And this is just an example of some of the POPS measurements from this campaign, looking at the particle concentrations as a function of wind direction, and then color-coded by the estimated LCL height as a proxy for boundary layer depth. So a few things that stand out, there are some clear directions, wind directions, that are dirtier than others, primarily here to the east and northeast. So those of you familiar with this area, there's a lot of refining activity going on in Texas City, along the canal and along Galveston Bay. Additionally, there is some down in this area as well, near Lake Jackson and Freeport. So you can see we have these dirty sectors. I will say that this one was a bit of a surprise. We still haven't fully figured out what lurks directly offshore, but my guess is it has to do with a lot of the shipping that comes out of the ship canal in Houston and starts to steam towards the south. The other thing that you would expect to see is that you have higher concentrations for the lower LCL heights, just because you have less boundary layer for that to get diluted over. So if you look at a given wind direction, the blue dots are higher, and the more yellow and red dots tend to be lower in general. Although that does flip upside down a little bit for these southerly wind directions. So that's potentially related to the sea breeze, although we haven't fully figured that part out yet. Just some more examples of TRACER. We had the luxury of flying through a wildfire plume. That was a wildfire that started, this was during a drought period in southern Texas, and there was a fire that started in the wildlife refuge, and we were just flying as this fire was starting up. So this is very fresh emissions, and you can see we were flying in and out of that plume over the course of the flight. We kind of mapped it out spatially and looked at the scale, the differences in size distribution inside and outside of the plume. And I put this figure up there because this is kind of a representative day for us from the TRACER campaign. We were out there flying between early June and late September, 2 weeks of each month. And each day we tried to conduct 3 similar flights over the course of the day. This particular day had 4 flights because we had to bring the aircraft down to a heavy precipitation event in the middle here. But you can see some of the features here if you look at the different variables: temperature, moisture variables, so humidity, wind speed, wind direction, and then the particle concentrations from the POPs, as well as the IR temperatures looking up, so you can kind of get a distinction between the more cloud-covered conditions and the clear conditions based on that upward-looking temperature sensor. A couple features, we had the sea breeze front coming through early on in the day, and then we had this precipitation event. You can see the precipitation event clearing out the atmosphere with this gradient in the concentrations. And that, of course, is also a combination of both the boundary layer development and the precip, but there's a very clear shift from these more yellow and green higher concentrations between, say, 200 to 400 per cubic centimeter to much lower values later in the day. I'm going to shift gears a little bit. So thinking about turbulent kinetic energy and trying to bridge measurements from a variety of different campaigns. This is a kind of reworked figure from Roland Stoll's book. This was from an online version. I think he's been working on this for a while, but it gives a nice indication of some of the different drivers of TKE in the atmosphere. So you have the buoyant production kind of on the horizontal axis, the shear-based production on the vertical axis, and all these different regimes based on what sort of atmospheric conditions you have, and then some indication of the kind of types of eddies and circulations you may have in each of these regimes. And so on the aircraft, we have a variety of different sensors that can help us to measure different terms of the TKE equation, and specifically I'll focus on the advective and the buoyant production terms here. And so just talking about which measurements we're using for that, I think it's relatively straightforward, but just to be specific about this from the perspective of the Raven, we're using a combination of the multi-hole pressure probe, the IMU, and the GPS for being able to calculate the wind quantities at the aircraft. And then from a thermodynamic perspective, we're using the measurements from the Weissler sensor, the cold wire, and the VN300, our onboard IMU, for a secondary source of air pressure information. To look at these terms individually as we're flying these constant level legs so that we can collect statistics over the course of those flight legs. The campaigns that we're looking at for this particular evaluation include the atomic campaign and the tracer campaign that I've already talked about, as well as an effort that we conducted in Wisconsin in the summer of 2021 at the Chewacki Prairie area, where we were also looking at coastal circulations and their impact on ozone advection. And I use these three campaigns because we were flying the same aircraft and the same patterns, and specifically these are very similar to both the tracer and atomic patterns, where we conduct an initial profile and then do these level legs where we spend a given amount of time at a given altitude. These are just two different flights. They're generally doing the same thing, right? You've got these longer legs and then the individual profiles. So I'll just give an example from one particular day here, in one particular flight. This is a profile of wind speeds that were measured on this flight based on the color coding. Don't mind the lines here, they're just giving you an indication of the altitude sampled for each of the parts, but you can see increasing winds with altitude for this particular day, as you might expect. These are just some of the individual terms, and you're thinking about the buoyant production of TKE. You get the virtual potential temperature, the vertical velocity perturbations, and then on the right here is this buoyant energy production term. So you can see higher levels of production near the surface and in the middle of the layer, and then lower levels of production up above at higher altitudes. If we transition to the wind shear production term, again, some of these initial quantities shown here, and one of the challenges that we run into, which comes out of the fact that we didn't particularly target this specific measurement as part of this campaign, is that we don't have a great representation of this shear profile, right? The vertical wind shear profile. Ideally, you'd have the Raven doing its statistical legs and then have another platform that's kind of continuously measuring the wind shear in the atmosphere. And so there are a couple of different ways that we can go about estimating this. I won't get into too many details here, but this is kind of similarity theory based, which has its drawbacks. But you can start to derive these kind of wind shear profiles, and I've compared them here to the measured wind shear profiles for this particular day from our individual profiles that we did. So in this particular case, it's not too far off of reality. But anyway, you can apply this and again, look at the TKE production from wind shear, of course, quite high near the surface where you have a significant shear gradient, and then decreasing with altitude. We like to look at the influence of local circulations on some of these things. So this is an example from Tracer. You've seen this figure already in the top. The bottom here represents the wind direction over time. So you can see initially we had kind of westerly wind coming from the land surface and then transitioning into a sea breeze regime coming off of the Gulf of Mexico. And we were wondering what sort of influence the sea breeze might have on these TKE generation terms. So here you see the first and the last flight of the day. Again, color coding is showing the wind speeds. Initially, we have low wind speeds near the surface increasing with height, and then later as the sea breeze develops, we have higher wind speeds near the surface. So in the rest of these figures, the triangles are the sea breeze, the circles are the pre-sea breeze environment. And so we can look at some of these same kind of terms again, and so you can see that in this case, this is largely a buoyancy-dominated TKE generation regime near the surface in the pre-sea breeze environment. And so these are just the individual terms, or some of the individual terms that contribute to this TKE generation. If we look at the sea breeze, things change quite a bit. Not so much for the shear, even though we have a very different looking wind profile, that the actual shear from height to height doesn't change that much. But we do get substantially more buoyant production throughout the column. And there are a couple of reasons for this. One is that you now have a slightly cooler air mass advecting over the same warm land surface. And secondly, not only is that same warm land surface there, it's actually warming more because you've eliminated the cloud cover. You have more direct solar irradiance to that surface. And so that gradient between the surface temperature and the overlying atmosphere increases pretty dramatically. You can start to put things together in the same kind of diagram that I showed initially from the Stoll book. This is looking at TKE generation, combining, again, the buoyant production and the shear-driven production for the different campaigns, so Tracer and the SGP flights that we conducted in the top here, and then Atomic and Wisco Disco in the bottom. I haven't done a lot of additional digging on this, but it's nice to start to put these pieces together. It's something that I've always really admired about Chris Farrell's flux work, that he has all these different campaigns and he starts to put everything together into single equations based on, you know, thousands of hours of measurements. So that's kind of the direction that we'd like to take some of this into. And you can start to look at relationships between, for example, the TKE and the vertical velocity variance. And you start to see kind of consistent relationships here between the different campaigns that are kind of scaled with wind speed. All right, I'm going to shift gears a little bit, and let's see, it's 4:05. Okay, I've got a little bit more time. So another recent campaign that we conducted, I think I mentioned this at the beginning, was here in the state of Colorado. This was the SPLASH campaign. SPLASH is the study of precipitation, the lower atmosphere and surface for hydrometeorology. For SPLASH, we partnered with the Department of Energy, who were also conducting a campaign called SAIL, as well as with EOL and others who were out there for part of this time as part of the sublimation of snow campaign, the SOS campaign. And we deployed instrumentation across the East River watershed near Crested Butte. It's a beautiful part of the state. If you haven't been out there, I highly recommend a visit. And the map here shows where we were located relative to the rest of the state. And then if you zoom in on that box, you can see that we had instrumentation kind of distributed across that valley. We also had some UAS operating primarily at this site, AYP, which is the Avery Picnic site just north of Gothic, and then at the Kettle Pond site just south of Gothic. The aircraft that we were operating there, we had two different ones. One was a hexacopter that was developed here at the University of Colorado. This system is equipped with a pair of custom pyranometers, one upward and one downward. These are stabilized on gimbals so that they stay level relative to the surface. It also had on board a multispectral camera, downward looking, to map out what we were flying over. This system was primarily deployed to collect albedo information and understand how that was changing during the melt season. And then we also worked with Black Swift Technologies here in Boulder to deploy their S2 aircraft, which was equipped with a microwave radiometer measuring soil moisture along with a camera system to look at other surface properties. So these are some of the examples of the sorts of data that we were collecting during the campaign. This is over the Avery Picnic site. And you can see on the left here, 2 different flights in the same location, 3 days apart. I'll talk about this case a little bit more, where we had a very dramatic shift in the surface albedo. Both of these are snowpack. This is just very dirty snow with a little bit of river starting to open up around it. And then on the right here, a few other quantities, including the volumetric soil moisture content, the surface temperature, surface elevation, and the normalized difference vegetation index to look at plant properties. These 4 were taken at a very different time. This was not a snow-covered time. So talking a little bit more about this albedo case that we sampled, we had some very, very intense dust and snow cases while we were out there. And you can see, it might be a little bit faded, but on the left here, some examples of the kind of dirty snowpacks that we were sampling. This is looking at this area in early March. We had a very clean snowpack at that point. Albedos above 0.7, in the 0.85 to 0.9 range that you'd expect for clean snow. You can see the shadows of these pine trees showing up very nicely. You get 3 little pine trees that are casting shadows that are picked up. Then we came back in April, and on the 18th of April, we flew over this area, and the snow was still relatively bright, kind of in that 0.65 to 0.7 range, and then each day it got progressively dirtier. And this was dust coming up through the snowpack as the snowpack was melting. There was still around 1 meter of snow on the ground here on the 21st, so it's not like we have bare ground coming through. It's just really dirty snow with albedos in the kind of 0.45 to 0.55 range. And like I said, some of the river starting to melt out, and you have open water coming out through some of this as well. Really interesting to look at that sort of progression and getting the spatial information, because oftentimes we deploy systems like this in the top left. This is an automated surface select station deployed by NOAA, collects a really nice data set, but for this particular campaign, it happened to sit over an area that was known for drifting. So when we look at a comparison between our albedo measurements and those albedo measurements, there's a very clear shift in the timing of the meltout just because it happened to sit over this kind of drift area. Another thing that we did with the Helix system, the hexacopter that I was showing, is fly over some tree canopies to better understand the albedo of trees in the wintertime. Part of this was driven by the fact that our initial measurements were always seemingly brighter than what was coming out of some of the NOAA models that we were looking at. And so we were trying to figure out if we were just missing something in our sampling or whether it was really a model-derived problem. It was probably a combination of both. But I'll walk you through this particular flight. So the points here are also labeled here. We start out near the road, taking off. That's here where we have the helipad albedo, about 0.45. We take off. As we increase altitude, our footprint increases. We see much more of the snow surface. This was a dirty snow surface. We're seeing 0.5 roughly albedo. As we climb, we see more and more of that, some more of the vegetation coming up. So you have this slow decrease in the albedo that's measured. Then we transition from this 0.1 to over the initial aspen tree area. And so that's this leg here. Aspen trees, we descended down over the aspen trees, which had an albedo of roughly 0.3. These are, of course, very leafless trees casting some shadow over the snowpack, but there's no real vegetation there. It's more about the shadow of the trees themselves. We climbed back up and we flew over the pine trees on the bottom part of that image near 0.5. They have, of course, a much darker look to them, and so this is kind of the pine albedo. And these measurements were calculated at as close as our pilot was willing to go over the tree canopy where he could see the aircraft. So it's probably about 5 to 10 meters above the trees. So that now you're talking about a much darker surface. And then we flew back home. So kind of unique measurements. I think we should do more of this to better understand the influence of different vegetation types on surface albedo, and so we can parameterize this a little bit more efficiently in our models. Shifting gears pretty dramatically from the mountains of Colorado to Lake Michigan. This is a campaign we conducted this summer. I'm not going to go into too many details here because we're just starting to dig into the data, but this was the Mitten CI campaign, the Maritime to Inland Transitions Towards Environments for Convection Initiation. This was led by Jason Keeler from Central Michigan University, and we played one small part of this campaign sampling the over lake environment during the lake breeze initiation. And so there were many other aspects to this. This is a very small figure, but we had flux towers, we had vehicles doing transects inland across the lake breeze front and boundary. And this is just an example of one day of our measurements out over the lake. We were doing very regular profiles, roughly every half hour or so. So you can see in this particular instance, we had a low-level jet transitioning into this lake breeze condition, very clear shifts in the mixing ratios over the near shore lake environment as well. One other campaign I'll mention from recent flights is the WMO UAS demonstration campaign. James Pinto from NCAR has been very active in helping to lead this effort. This is something that came out of the World Meteorological Organization, and it's meant to be a way to demonstrate the influence of UAS on weather forecasting at a larger scale. So we had teams all over the world operating systems during particular intensive operations periods, and we contributed both in the springtime in April as well as in the fall in September to this campaign. We flew a variety of different systems. We also put all of our Michigan measurements from this Mitten CI campaign into the database, and there's now a very large collection of UAS-based profiles and measurements that are archived by the WMO for ingestion by weather prediction entities around the world, and this is very much in progress. If you want more information, please seek out James and ask him some questions. All right, looking ahead a little bit, I don't know if any of you read these MIT Essential Knowledge series books. They're nice, they're relatively compact, and they tell you, at a very entry level kind of what's new in the world. You can find them on a variety of different topics. These are just some examples that I think are very applicable to the sort of work that we're doing. You can see some things that might look familiar: 3D printing, spatial computing, data science, et cetera. And I think we're kind of working towards the next revolution, which combines the robotic systems that we've developed, the very small electronics that are continuing to advance, and continued advancement in battery technologies to increase our sampling efficiency. There's a group in France that's working on having real autonomous sensing of features. So this is work by Mari et al. Looking at autonomous sensing of cumulus clouds, and this is something that was happening in Barbados while we were down there flying. The French team was launching their aircraft, saying, okay, it's all you now. Go find a cloud and fly around in it for a while, and then when we tell you to come back, come back. And it worked. I mean, it was pretty cool to see, because the aircraft would go, they'd point it to a cloud, but once it hit the cloud, it would be doing its own feature finding to kind of sample the cloud as efficiently as possible and stay with it. And then after some amount of sampling and the kind of battery usage, it would be told to come back and it would return to home. But I think we need to do a lot more of this. I think these platforms are primed for this kind of sampling. You can picture similar things with regard to thermodynamic boundaries, whether it's sea breezes or just the boundary layer top or something like that, or emission plumes, things like this. I think that we have to start letting the robots be a little bit more robot and do their own things. I'll also really quickly mention another campaign that we're engaging with, which is the CROCUS, the Community Research on Climate and Urban Sciences campaign, that's been going on for a while now in Chicago. This is one of the Department of Energy Urban Integrated Field Laboratories, and this effort is led by Argonne National Laboratory in collaboration with a variety of universities in the area. They're very interested in, of course, the kind of urban coastal boundary in an interface, and have engaged us to try to collect some of the spatial information that's challenging to sample with ground-based sensors. I'll say very briefly that urban environments are quite challenging for these platforms for a variety of reasons, but one of those has nothing to do with the actual atmosphere, and has everything to do with just the amount of electronic noise that we have in urban environments and how our systems react to that. So this is very much a learning process for us, and of course with the infrastructure and the people around, it's also kind of a high risk, kind of high stakes environment to operate in. So we have to step into that very carefully. Finally, I'll mention that our team was recently awarded one of the NSF Community Infrastructure Facilities awards for our equipment. So this includes the Raven that I've talked about quite a lot. It includes a Copperson that we have within our group as well, and some of our surface systems, including the mobile ground station, the tracker vehicles you see on the bottom there, and our van that has its own 50-foot mast associated with it for operations. This SIF is called the Mobile Uncrewed Systems for Atmospheric Science effort, MUSIS. That wasn't my selection, but it works. And so these facilities are now, or this facility is now requestable as some of the local facilities here are. When people put in field campaign requests, they can ask us to join. And we're very excited to be part of that pool. I think it opens up a lot of doors for kind of combined sampling with a variety of different sensors, and certainly we look forward to working closely with NCAR in many of these future campaigns. So very quickly to summarize, we have been using small UAS to provide detailed perspectives on the lower atmosphere, including in areas that may be challenging, difficult, dangerous, et cetera, for larger research aircraft or other sensors. We've been deploying these systems for over a decade and have a good amount of expertise and knowledge, both in terms of the systems, the measurements, but also in terms of airspace access and things like this. We've deployed a variety of different platforms all over the world to get insight into physical and chemical processes governing weather and climate, and we're continuing to push our boundaries when it comes to technology, endurance, sensor systems, et cetera. I will say very quickly, we found that these platforms are really great for educational purposes. They're engaging, people are excited, they can connect to the smaller things a little bit easier in some ways, and you can watch the aircraft do its thing locally. And so we really want to try to leverage that to the extent possible and make sure that we're sharing our experiences with a variety of different audiences. And finally, I'll just acknowledge the different funders, the kind of usual suspects, NOAA, NSF, DOE, but also some of our national laboratory partners, PNNL and Sandia. And for anyone who looks at this later, there are references. So you can't read them now, but they're there. So thanks very much for being here. I appreciate it's a day that many people are distracted, so I really do appreciate your attention for almost an hour here. Thank you.
Thanks, Gijs, for that really interesting seminar. Very broad depth of topics. Quick reminder for those online, you're welcome to enter your questions in Slido if you just scroll down below the video screen. Do we have any questions from the room?
Hi, Gijs. I really enjoyed the overview today. It's a lot of fun, exciting to see. And it's great to see how the technology is really continuing to advance. Curiosity, where do you see the future with the technology in regards to, say, more adaptive flight patterns? Because I'm assuming both missions, there's a fixed pattern defined ahead of time. And what I'm kind of getting at, whether it's machine learning, AI to be more adaptive down the road, but a little bit more forward thinking with the AI and machine learning for flight patterns for any of these vehicles.
Yeah, I mean, that's what I was definitely alluding to with the cloud sampling. Again, the aircraft is doing its own reacting on its own to the measurements that it's collecting along the way. And so that's all happening on board on the small microprocessors that are flying on these small aircraft. So it's a big part of the equation. There are groups at CU, Eric Frew, for example, has an autonomy group that's looking at coordinated sampling, right, where the aircraft are all reacting to each other and talking to each other and trying to sample things in a specific way. So there's a lot that can be done there. That was also part of the motivation for that van that I showed. That has its own server rack, and so you can imagine these systems talking to each other, but also then communicating back to the van and having some more powerful computing resources close by but not on board during flight operations.
Yeah, I understand you're pretty focused on the small UAS. but I'm kind of curious because a lot of species, particularly chemical species, can only be measured with heavier instrumentation. What's the payload of the systems you're flying, and then what do you see as opportunities or challenges for flying something, say, a factor of 2 to 10 heavier?
The payload question is always a tricky one because we can always trade off, right? And so when we integrated POPs, for example, onto the Raven, we took out a little bit of our battery. We just had a slightly smaller battery pack. So typically we fly things on the order of a kilo or 2 and not much more than that for the Raven. We do have a larger version of the Raven that we've operated with a little bit more. So for example, a CDP on board to look at cloud droplet properties in addition to a POPs and some other sensors, but still relatively small. For the larger aircraft, I do very much think there's a role there. I have conducted experiments with the Global Hawk, the largest of aircraft with Terry and others, but also with, for example, the DOE Arctic Shark and other kind of medium-sized, let's say, aircraft. I think the thing with those platforms is that they can carry more instrumentation. They can provide in that way a more comprehensive perspective on the atmosphere, but there's also a trade-off when it comes to risk. And so once you start flying heavier and more expensive things, people are less likely to want to put that down at 10 meters above the surface or over a populated area or whatever sort of risk you might want to introduce. So I think putting pieces together and combining the different assets can be very powerful. So if you have one of the larger UAS sampling, let's say from 200 through a couple kilometers, 200 meters to a couple kilometers, something like that, and you have the smaller UAS bridging the gap to the surface or some combination of that, and maybe even some larger crewed research aircraft in the mix as well, that can be very powerful. Cost goes up, of course, but there are roles for all these things. Yeah.
Great question.
Two things. What's the maximum wind speed you can fly around in, and how long does it take to make a vertical profile?
Yeah, so from a wind speed perspective, for the Raven, very specifically, that aircraft has a burst speed of up to about 80 miles per hour. It won't fly for very long at 80 miles per hour, but for the fixed wing platforms, if you have the airspace and the ground space, there's no reason they can't fly backwards, right? So as long as you can launch it, it's perfectly happy maintaining its airspeed and getting pushed backwards as long as you can stick with it. So I always hesitate to put a firm number on that because it really comes down to the mode of operation. But if you want to have something where you're flying comfortably and staying in one place and not moving around, once you get above 25 meters per second or so, your endurance starts cutting down pretty dramatically. So for example, when we were flying for the WMO campaign, we were up in the Pawnee National Grasslands. We were doing an early morning flight. We climbed right up into a low-level jet. We kept climbing, kept increasing the airspeed, kept climbing, kept increasing the airspeed. Once we hit 26, 27 meters per second, we decided that we weren't going to be able to fly long enough to keep doing that for enough time to make it worth it, and we brought it back down. From a launch and recovery perspective, when it gets above 20 meters per second or so, it gets a little spicier.
So we have a question online.
There was a second part to your question.
Oh, how long does it take to make
Oh, yeah, good question. So typically we like to conduct the profiles relatively slowly because we want the sensors to be capturing many of the features as we can. We usually do roughly 2 meter per second ascent and descent rates, but that can be increased to about 5 meters per second if we want to.
Good recall.
Yeah.
So we have a question online from James Pinto. Where do you see FAA regulations going in the next 5 years to allow more flexibility of sampling strategies, including deeper profiles and BVLOS operations over the U.S. using small UAS?
Yeah, thanks, James. That's a good question. I can't speak for the FAA. I can't speak for NOAA. I can't even really speak for CU. I think I can just speak for myself. I would say that the FAA has made some pretty substantial changes over the last 5 to 10 years. I think Even 5 years ago, things were a lot more complicated, and they're becoming more streamlined in the domestic airspace. When we talk about beyond visual line of sight, I mean, that's happening already, right? There are small UAS flying BVLOS in certain regions, and I think more of that will happen over time, but there's very much an element of demonstrating that you can do that safely before it's going to be just widespread permission for everybody to do it. So will continue to kind of be small steps in that direction, but once you have demonstrated your ability to conduct those flights, I think there is a willingness on the FAA side to begin to integrate more of that into the airspace. So I can't give you an exact timeline of who's going to be doing what when, but I do think that more so than a few years ago, there's more willingness to recognize that this is going to happen, and more of it will happen over time, and we need to continue to figure out ways to do it safely.
Any more questions from the room?
What sort of observations are you targeting for your UAS DC project? Like, is it routine profiling? Are you looking in particular locations, and how are you determining those locations?
Yeah, so the UAS DC is kind of a unique thing, right? Because, well, I'll say that there were very few groups that were actually funded specifically for that activity. And so in some ways, it was very much about leveraging people's existing activities or planned activities and trying to coordinate it in a way to get all of the observations into the same format, into the same place, et cetera. Having said that, for our UAS DC flights, we were primarily focused on frequent profiling, both in our flights at the grasslands as well as in our flights in Michigan. It was all about up and down frequently. I think that was primarily what most of the groups did. I'm trying to think of examples where that wasn't the case. I will say that the September intensive operations period that took place was part of a broader effort in connection with the International Society for Atmospheric Research using remotely piloted aircraft. Yes, it is a real group. ISARA is the name of the entity. I think there may even be a water bottle in the room somewhere that has the ISARA logo on it. There we go. Two of them, all right, excellent. So it's a really good group, but they also like to do it with their annual conference, a flight week. And this last year we were in Oklahoma in September, and we conducted a variety of different experiments around northeast Oklahoma. There were groups around Tulsa doing urban heat island and turbulence studies, and then a kind of broader distributed group that were doing regular profiles with the mobile not mobile mesonet, just mesonet sites in the area. And so there it was kind of a combination of more of the statistical sampling and the frequent profiling.
Good question. Any others from the room? Last call. All right, if there's no other pressing questions, Gijs, thanks again for that really interesting
Thank
seminar.
you. Thanks.